Welcome to 1100. We are doing Archimedes principle today, and right off the bat I want to tell you it is hot as hell in here and I'm going to start sweating. It's 100 degrees outside. I've turned off my air conditioner so that we have good sound quality. So if I start sweating, that's what that's about, and excuse it please. So let's get started. Before we do, I want to talk about our equipment a bit, and we would typically be using this balance. This would be provided to you in your lab. Now, what we do is we suspend this on a post so that it is elevated. We tie a string to this bottom hook here, and on the end of that string is our mass. So that's one way of weighing it. Instead of putting it on top, we just hang it from the bottom. Now, the reason we want to do that is because we want to take two measurements, one where it's just in air and the other where it's submerged in water. So we want to weigh it while it's submerged and not weigh the water, right? So that's why we can't put it on top. So this is suspended. Our mass is hanging from a string to a hook on the bottom of this pan here. I discovered that this has more air than we would like. Typically, when you're reading a scale, to determine the amount of air associated with that measurement, what you do is you take half the value of the smallest tick mark. Now, these smallest tick marks are 1/10 of a gram, so half of that is 0.05 grams. So our measurement, our air in our measurement will be plus or minus 0.05 grams. Now, we can't use that air when we make measurements with this balance, because if I measure a mass on this, I can tap this over up to 0.3 grams, and when this will oscillate a bit slightly, but when it comes to rest, the needle will not be in any discernible different spot than before I moved it. So you can see how the air is much greater than 0.05. It's like, well, 6 times larger than that. It's 0.3. So there's that. And the other thing is, I had a sample mass that weighs approximately 200 grams. And when I weigh it on this, it is measuring like 0.7, 0.8 grams less than what I think it truly is. So this isn't too accurate. I was thinking, okay, well, we'll just subtract that difference from our measurements. But I don't know if it's weighing less at a particular position on the scale or range of the scale. Like when we weigh something heavier, which we'll do in the lab, it may not be off that much, or maybe off even more. So I'm trying to figure out exactly how to determine in which way it's off and make corrections for those, but I just gave up and abandoned it. Hey, I need to make this video, right? So we're going to use a digital scale today. That digital scale, per the manufacturer, gives us an absolute error of plus or minus 0.01 grams. Now, I wanted to calibrate that. It's been around for a while, so I wanted to calibrate that so that we could comfortably accept that the true error in our measurement is 0.01 grams. But I don't have a calibration weight. Well, I do. I thought I did, but it's too heavy for that particular scale, so I can't calibrate it. So what I'm thinking is, to play it safe, I would say we'll read that to the tenths of a gram and have an error associated with that with plus or minus 0.1 gram. It's just uncalibrated. I just don't trust it. I don't think it's reliable. But actually, we are going to add some error associated with that instrument, and I'll talk about that in a few minutes. So anyway, let's get rid of this. Okay, done. Out of sight. we want to determine the volume of a cylinder in two ways. The first way is just by measuring its diameter and length. Actually, outer and inner diameter, because it is a cylinder with a hole in it, a hole down its center. So we can easily determine the volume by measuring it. Then what we'll do is calculate the volume of that cylinder using Archimedes' principle and compare the two. So let's get started, and I'll put you on pause. So we may be doing this in a different order than your lab manual outlines, but doesn't matter. We're getting the same measurements that they're asking for. First of all, what is the mass of this cylinder? So I have it here suspended on the bottom of a hook on this digital scale. So that's another way of measuring the mass of an object instead of placing it on top of the pan here. And I am getting a reading of 363.37 grams. And let's say it's 363.4. What we'll do is we'll round to the nearest tens place. And again, that's because we don't know how well this instrument is currently calibrated. What I want to mention is that technically, I'm not measuring the mass of the cylinder. I'm measuring the mass of the cylinder and the string, or in this case, dental floss that it is tied to. So for that mass I just gave you, make note that that is for the cylinder and string. Now, let us determine the apparent weight when it is submerged. Okay, since it is swinging, I'm getting a reading that's fluctuating a bit, so we'll wait for this to come to rest. I don't know if you could see, but, well, yeah, sure you can see there is some ice in that water container. Now, when you're doing one of these, when you're doing the analysis, it calls for the density of water. Now, I'm going to assume that you're going to use 1, right? 1.00000 grams per cubic centimeters. Now, the density of water, strictly speaking, well, it isn't a constant. It fluctuates over the range of the temperature of the water. From 0 to 100, not significantly, but nevertheless it does. So just to eliminate other sources of error from our experiment, I threw some ice in there and cooled the water down to close to 4 degrees Celsius, which indeed gives us a density of 1.00000 grams per cubic centimeter. And I could have just given you the temperature of the water, then you find out what the density of water is for that particular temperature, but 1 is a nice round number. I'm trying to make this easy for you. So you could use 1 for your density of water. And it has come to rest. Let me read the scale. So instead of like moving the camera and pointing it above the scale, you could just trust me, right? It is 320.37 grams, or in other words, 320.4. So I'm going to write that down as well. 320.4 grams. Now, let's consider this string. Half of that string is submerged in the water. So let's consider the string that isn't submerged in the water. The portion of the string that is not submerged in the water is going to contribute to the overall weight of that cylinder. So we want to subtract that. So bear that in mind. The other half, we're just going to neglect because of the buoyant force. There's a force pushing up on that dental floss, and actually the buoyant force is probably greater than the gravitational force pulling down on it, right? I mean, if you just threw that dental floss in the water, it would float. So it'll introduce some air, but not by much, and we'll take that into account. Of course, we made the approximation that only half of the string, we're only going to subtract half of the string because only half of the string is not in the water. That was a guess, plus because like I just mentioned, there's going to be an overall net force in the upwards direction from the string that is underneath the water. We're introducing more air. I think we'll determine the mass of that string. I think it's about 0.14 grams. Half of that is 0.07. I would say for our mass reading, how about we just do an overall absolute air of plus or minus 0.2 grams. Before it was plus or minus 0.1 grams, but because of the issue with the string, we'll add another 0.1 to it. So our overall air is plus or minus 0.2 grams. Now what we need to do is measure, let's go ahead and measure that cylinder without the string, or simply just measure the string. Let's figure out what the mass of that string is. Let me put you on pause. All right, so we are weighing the mass of the string. I don't know if you can see it. That dental floss is on the hook by itself without the cylinder attached to it. It's right there in the center, and we are getting a reading of 0.13 grams. So let's make a few corrections. Give me a second here. So for our original measurement, the cylinder with the string, we got 363.37 grams. So what we're going to do is subtract the mass of the string, which was 0.13. So that gives us 363 rounded to the nearest tens place is 0.2. 363.2. So that's one of your measurements. That is the mass of the cylinder as it is just in air, right? 363.2 grams. Now, when we submerged the cylinder, it was weighing the string as well, but only half the string. So let's subtract half the string from that. I didn't record what that value was to the hundreds place. I immediately rounded to the tens place. Technically, I should have saved that for this subtraction, but I didn't. Anyway, we're going overboard anyway, being meticulous, so that's not going to hurt us. We want to subtract half the mass of this string, which is 0.065 grams. So that gives us, for the submerged apparent mass of the cylinder, 320.3 when we round to the nearest tens place. So taking that string into account, we drop the submerged case by 1/10 of a gram, and we decrease the plano mass measurement by 0.2 grams. So again, since we're doing propagation of error, why not eliminate all other sources of error that we're not taking into account? So that's why that's why I'm dwelling on this. But there are your two measurements, and that's it for this part. Now let's find the density of a block of wood, which is going to be easier. On to part 2, density of a block of wood. So I already weighed the wooden block. I didn't hang it, I just put it on top of the scale. And the mass of the block is 18.58 grams, or 18.6 grams. If we continue to, which we should, continue to round to the nearest tens place, and then the air again will be plus or minus 0.2 grams. So that is the density of the wood. Now, as it stands right now, wood and cylinders tied together. The cylinder, however, is the only object submerged in the water. So this scale reading is 339.46 grams. 339.46 grams. Now what we want to do is submerge both objects in the water. So bear with me. Swinging around a bit, so it's fluctuating. We'll wait for it to stop swinging. By the way, part A says measure the mass of the wood block in air. Then in parentheses, you do not need its dimensions for any result, but they might be handy to check for gross errors in the Archimedes volume measurement that you will use. So, okay, why not? We'll measure the dimensions of that wooden block. I am not going to use a vernier caliper, however. That thing is way too accurate to measure the dimensions of this block. And I say that because this block is old. It's been, it's somewhat waterlogged. It's been submerged in water so many times. It's kind of deformed. The edges are worn away. The two sides aren't even perpendicular completely to each other. Plus there's a hole drilled in the center and on the outside, on the surface of those holes, the wood is really worn away, so it doesn't make any sense to use a vernier caliper to measure that volume. What I'll do is I'll just get a simple ruler and measure one side, and then you can determine, you can approximate what the volume is. If you want to check for, like the manual says, any gross errors in your Archimedes volume that you come up with. So let's see what this weighs in at, and that is 286.84 grams. Okay, let's see. Oh, there's one part where it says to measure, part B, measure the combined mass with both in the air. Now, personally, I don't know why they want you to do that. I don't know how you use that information for anything in your analysis, but okay, maybe I'm overlooking something. I can't remove this and weigh those two objects hanging there. The reason being is that I would damage the scale. There's a limit to it, 400 grams, and these two objects would exceed that. So, oh, I know. The mass of the wooden block, we already have that. That's 18.58 grams, and this cylinder, we already did that measurement, the mass of that cylinder for part A, the first part. So you can just add those two and get those, find what that result would be if by chance you need it, but again, I don't think you do. The only thing is we didn't take into account this new string that I used. We don't care about that because this part of the lab is just an approximation. Reason being is that you have nothing to compare your final measurement with. You're determining the density of that block, but we don't know what the true density is. I mean, if it was an actual block, geometrically speaking, if it was a cube, we could determine its volume and then determine its density, but it's misshapen. Plus, we have no idea what kind of wood it is, so there goes that. Anyway, that is all the information you need. Let's see. Let's get the dimensions of this block. So, just in case you need it, one, two, three, 3.7 centimeters. 3.7 centimeters. The length of one side is 3.7 centimeters. And you could see what I mean by that hole. It wouldn't make any sense to measure that hole accurately and subtract it from this block because this block is just too beat up. Now, that's it. That's Archimedes' principle. All you have to do now is analyze that data, and I'll see you next week.